All right, so we'll go ahead and we'll solve problem 3. They're giving us a starting material and telling us that it makes two different products and then the ratios. So they tell us that the reactants are 50% aqueous acetone. So putting that into normal reagents, aqueous means water, so it's a mixture of water and acetone, which looks like that. And it's 50-50. And if we kind of analyze what is in the products in order to figure out what's happening, I can see that I have in both of them, I have an OH that's been incorporated. So there's an OH. And in my reactants, I started with a chlorine. Now I do see a double bond in the products, but if I take a look at the reactants, I also see a double bond there. So double bond, double bond, double bond. So I haven't created a double bond. It's still in the products. It just has been moved. And so I don't need to worry about making a new one. It's just a question of relocating the current one. So given that, the fact that I am turning a Cl into an OH, we can tell that it's a substitution reaction. And since I have water and acetone, the acetone is not being incorporated into the molecule. There's an OH, so pretty clearly the water is the nucleophile, and it's the one doing the reacting, and it's a poor nucleophile. So between the poor nucleophile and the fact that I have a double bond moving around, in other words, there's a rearrangement of that double bond, everything is pointing to this being an SN1 type mechanism. So they say write out a detailed mechanism for this. So let's go ahead and let's just do that. We have CH3 and a CH double bond CH, CH2Cl. And I'm going to go ahead, and since it's SN1, the first step is you lose the leaving group, so chlorine leaves. And that's going to give me a carbocation, so a CH2 plus. Now it's a primary carbocation, so it's not that stable if it were just primary, but it's not just primary. You can see that it is one removed from a double bond, so it's actually primary allylic. And so because of that extra stability, this will actually form in a reasonable manner. Now, primary allylic carbocations are resonance stabilized. And we're going to take advantage of that and draw the resonance structure. So to draw that resonance structure, I'm just going to move the pi bond. So I'll take the double bond and I'm going to move it over there. And we'll just draw that resonance structure right here. So it's going to be CH3, CH, and then there's another CH double bonded to a CH2. So that's the new location of my pi bonds now at the end. And the plus charge has been relocated to one of the internal carbons. So that just basically shows the delocalization of that positive charge. This also is going to lead us to our two products. So from my first structure, let's call it structure A, and then we'll call the other one B. From structure A, if I take and have water react with it, let's go ahead and show that. So water would come in with its lone pair, and it would attack the carbon with the plus charge. I would have a CH3, CH, double bond, CH, CH2, and now it's bonded to what was water, so OH2 with a plus. And all I have to do then is I'll lose that H+. The way it gets lost is another water molecule comes and just grabs it off of there. That would give me CH3, CH double bond, CH, CH2OH. And if you take a look, that is the first product, and they say that's 56%. That's product number 1. Now, product 2, the double bonds at the end, and the OH is kind of in the middle, that's coming from the second resonance structure. So if I take the second resonance structure and water attacks it, so I would have my OH2 lone pairs here. They're going to come and attack that carbon with a plus charge. I would have a CH3, a CH. That CH is now connected to water, which has plus charge. And then CH double bond CH2. And likewise, we'll just lose H+. So again, another water molecule would just come grab it. Just deprotonate just like that. We would have CH3, CH bonded to an OH, going to a CH, to a CH2. That is, if you take a look, that's product number 2, and they said that was 44%. Now, as far as the percentages, you can explain that by looking at the location of the double bond. In product number 1, my alkene is di-substituted, and so it's more stable. And so that is going to be a little better than product 2, where my alkene is mono-substituted, not quite as stable. And so it's not going to be as favored. Okay, so there it is. There's the mechanism. It all tied into having the 2 resonance structures and then having the water attack at the carbocation of each resonance structure to give you the 2 products. This problem's an interesting one. Let's expand it up so we can actually see it. Okay, they sort of give us a little sort of mechanism layout before you actually get to the crazy problem down below. So what they say is you're going to make this thing called an epoxide. And the epoxide is just a 3-membered ring with an oxygen in it. And one of the ways to do it is to take a 2-carbon system that has a chlorine and an OH and deprotonate that OH. So we're going to deprotonate it with OH minus from KOH. And that OH minus will just grab the hydrogen, take it away, leaving us with an O minus, which then is a nucleophile. This is like, it's in, a strange looking molecule, but this is sort of like OR minus, isn't it? You have an alkyl group, a carbon, connected to an O with a minus charge. So it's a nucleophile, and it is going to attack something that has a leaving group, so it can do a backside attack because it's set up exactly opposite the chlorine, and it will kick out that chlorine, and then you've made an epoxide. So as far as the mechanism, it's just sitting up there. The mechanism is a nucleophile attacking a carbon and kicking out a leaving group, and it's a backside attack, so it is an SN2 mechanism. Specifically, it's what's called intramolecular, which means within the molecule. So you have an SN2 that's occurring from one part of the molecule attacking another part of the same molecule, and those make cyclic compounds. So it's an intramolecular SN2. The key thing to realize with this is to make this epoxide is that the O minus, the nucleophile, must be 180 degrees to that leaving group. They have to be opposite because that's SN2. Without that, you can't have an SN2. So then they lead us to this problem with all this writing, a lot of which we're actually going to ignore. So they tell us we have 3 different things. And the labels, of course, have fallen off or whatever it is, and we have to identify them. And they're different stereochemical permutations, sort of the same molecule with different groups cis and trans. And they tell us that when you treat the system with KOH and methanol, that the compound in bottle A gives no epoxide. It doesn't do it. So keep in mind what's going on in all of these. Notice you have an OH, and then right next door is a Cl, very similar to what was here on top. And so we could deprotonate the O, and theoretically it would loop around and it would attack the chlorine. Okay, so that's the kind of reaction that's going on there. So I'm going to erase all that because it got very messy. But there it is. So we just have an O- attacking a chlorine. That's the setup. And some of them are doing it, some of them aren't. So they say bottle A gives no epoxide. And they say that bottle B gives an epoxide. So bottle B gives an epoxide and bottle C gives an epoxide. So they both work. They say that epoxides D and E are stereoisomers. So instantly I'm intimidated, right? That's a little scary. I'm going to ignore it for now because maybe I don't care. That's what I'm hoping. Okay, the minute you read that sentence, everyone says, okay, I quit. Just ignore it. It might not be important. They tell us that C forms an epoxide much more slowly than B does. So C is slow and B is faster. I don't know how fast it is, but it's faster. So, okay. So what we're going to do to answer this is I'm going to take these rings and I'm going to put them in a chair form. And we're going to see if that helps me figure out this whole 180-degree thing that we need to deal with. So let's go ahead and let's do that down below here. We'll do number 1. Let's put it in a chair form. So I'll draw a chair. Now we know if we're doing a 180-degree attack, that the only way I can do something 180 degrees is to put that leaving group in an axial position. Otherwise, if I put it equatorial, everything's 60 degrees to it. Nothing's going to work. I have to be 180 degrees. So we are going to force that chlorine to be axial because it has to be. So I'm just going to stick it down just like that. There it is, axial. It is going to dictate where everything else is. Since it has to be axial for this to work at all, I have to put it there, and everything else just ends up where it ends up. Now the OH is next door to it, and notice the Cl and the OH on number 1, they're trans, right? Those two right there, they're trans. So if the chlorine's down, the OH has to be up. So we got that. I'm kind of liking the look of that right now. Then there's a tert-butyl group that is 1 away, and 1 removed. And that tert-butyl is also trans to the Cl. So if the Cl's down, that tert-butyl must be up. And it is on, not on the carbon right next door, but 1 more. So it's over here. So I'm going to draw it right there. There's my tert-butyl. So it's equatorial. So that's what number 1 looks like. Let's do the same with number 2. Draw a chair. And I'm going to put the Cl axial because it's leaving and it has to be axial. So it's axial. The OH is trans to it. So the Cl's down, the OH is up. That's looking pretty similar. The tert-butyl group is going to be cis to the chlorine now in number 2. And so the chlorine's down, so the tert-butyl's also down. So that will look like that. And then let's do number 3. So number 3 is another chair form. And I'm going to put the Cl down. The OH in number 3 is cis to the chlorine. They're on the same, going the same direction. So if the Cl's down, the OH is down. And the tert-butyl is trans to the chlorine. So if the chlorine's down, the tert-butyl's up. So it's equatorial here. So those are the 3. Now they tell us that one of them gives no epoxide, one's slow, one's fast. So keep in mind, looking back at the epoxide formation, remember that it is an SN2 reaction. I have to shrink this down a little bit now. Okay. It's an SN2 reaction, and it's going to require that the O- and the leaving group, the chlorine, have to be 180 degrees apart. So I have that set up in number 1. These guys are 180 degrees apart. One's straight up, one's straight down. I have it in number 2 as well. One straight up, one straight down. Look at number 3. I don't have it there. Those are not 180 degrees apart. And so this number 3, since these two right here are not 180 degrees apart, and the Cl would have to be axial in order to get something 180 degrees to it, this is not going to work. This is going to give no epoxide. And the reason for that is there's no SN2 possible. If I chair flip it, the OH is straight up, but the chlorine's equatorial, so they're still not 180 degrees apart. So number 3 will never work. So that's the one that gives no epoxide. The other 2 can give an epoxide because we have that 180 degree OH is exactly opposite the Cl. It's perfect. One is slow and one is fast. The answer to that lies in the location of the tert-butyl groups. If you remember way back when, large groups want to be equatorial. So they prefer the equatorial position. So that tert-butyl group, the most stable chair conformation, the tert-butyl's equatorial. Well, number 1 has the tert-butyl group equatorial. So this is the preferred conformation for number 1. Number 1 is perfect. I have the preferred conformation. The chair will exist in this form predominantly. It is going to be fast. Number 2, in order to get the OH and the Cl 180 degrees like they are, for that SN2 reaction, for it to occur, that tert-butyl is axial. That is definitely not the preferred position. And so this is going to be a difficult chair form to establish. Most of the molecules will not be like that. And so this is going to be slower because you're not going to have many molecules that are willing to put the tert-butyl group axial. So very few molecules will have the correct setup. So 1 and 2 will both do it. 1's perfect, fast. 2, tert-butyl's in a bad spot, and so it's going to be slow. Okay, on this problem, they're giving us a molecule and subjecting it to elimination reactions. In one of the reactions, we have the top one. we have a strong base, so we have OCH3 minus, which is a strong base. And then there's heat, of course. So the top one's an E2 reaction. And then the bottom one, I have a weak base, and the bottom one's an E1. Okay. And they give us some stereochemistry of the CH3s, the carbons with the CH3s. They tell us that the top one's R, the bottom's S. And the question is, what is the stereochemistry where the bromine is? So they want to know, using the information given, is the configuration at carbon 2 R or S? That's the carbon with the bromine at it. So that's the question. And then they want us to explain why the two reactions give different products. So let's first do the configuration. I'm first going to redraw what the CH3s look like so that I know if they're wedges or dashes. And so let's go ahead and let's establish that first. So I'm going to keep my life simple and easy. The bromine, I don't know. I'm going to just leave it alone for now. Don't know a thing about it. I'm going to put that top CH3 that should be R. I'm going to draw it. I'm just guessing. There's no reason I'm doing this in particular. I'm putting it towards me. I just guess that that's what I want it to be. The reasoning for that is it puts the H away from me. And remember, when you're doing R and S, the number 4 group has to be away from you, right? And so this accomplishes that. So I'm going to see what I come up with. And if it's R, I'm happy. That's great, right? But if it turns out that what I drew with the CH3 coming at me is S, which it needs to be R, simple enough, I'm just going to switch the H and the CH3. I just know I drew it wrong. So if you draw these, put the lower one in back, and then you can always switch it if you're wrong. So going through and doing our numbers, and let's do the same on the bottom too. Let's just go ahead and tackle that right away too. I'm going to put the CH3 forward. For no other reason than that, I want the H back. Right? Keeps my life simple. So let's do the top one. The H is number 4. The part of the ring going towards the bromine will be number 1. The part of the ring without the bromines 2, and the CH3 is 3. Let's see how I did. So I'm going to trace a path from 1 to 2 to 3, and that ended up being, it's clockwise, so it ended up being R. I was lucky. I had a 50-50 shot, right? So it ended up being okay to do that, so I don't have to switch anything. Let's do the bottom one now. H is 4. The part of the ring going towards the bromine would be 1. The other part of the ring is 2. Methyl's 3. So going and tracing a path from 1 to 2 to 3, it's going that way. And that is counterclockwise, so that's S. And that never happens, but I got that right too. Now, if it had been wrong, let's say the bottom one turned out to be R somehow, what I then would have done is just drawn the H coming at me in the CH3 going back to fix it. Okay, it turned out my first guess was right, so that's good. Okay, now, the bromine we don't know. It could be either coming away or going back, no clue at all. So I am going to make an assumption here. So I have something to work with. I will assume that the bromine is, I don't know, going towards me. Let's just test that out, see if that makes sense. So the CH3 is up towards me, and the bottom CH3 is also towards me. I know that's true. And I'm going to say, well, okay, bromine's towards me. Now, what I'm going to do is see if the molecule that I just drew fits the experimental data. If it does, that's the answer. If it doesn't, then I'm going to say, that didn't quite work, and I'm going to draw the molecule with the bromine going away and see if that is better. Okay, so let's tackle the E2 reaction first. And remember, with an E2, I'm doing the E2, I have to have the H and the leaving group 180 degrees. They have to be anticoplanar. So I've got to do a chair structure. So let's go ahead and let's do that chair structure of this guy. So there's the chair. The bromine has to be axial, and so I'm going to pick an axial position and stick it there. That has to be true for an E2 to work. There is a methyl right next door to it, next carbon over, and that methyl is cis to the bromine. So the bromine's down, so the methyl will be down. So I'm going to put that right here. And then not next door, so not that carbon, but the next one removed. So 2 carbons away is another CH3 going the other direction. And that is also cis to the bromine, so it's also going down. So I'm headed the other direction around the ring now. And not the carbon right next door, but the next one, so the one with the dot. The methyl is down. And so that is going to put it, I have to sort of, I drew this kind of small, puts it in the axial position right there. Okay, so now what you do is draw in the H's. So we'll put in the H's that are adjacent to the BR. There's one right here. And then there are 2. There's one here, and there's one there. And we're going to do an E2. The base is small. If you take a look at the base, it's methoxide. So I'm going to have OCH3, and it's going to remove a hydrogen. Since it's small, I'm going to try for Zaitsev. I would prefer to have a Zaitsev product. So I prefer the most substituted alkene if I can get it, right? I don't know that I can. That's just if possible. Now, when we say if possible, what we need is I need an H that is 180 degrees to that bromine. So it looks to me like I've got one. This hydrogen right there, where the CH3 is one that I could remove, and it is 180 degrees to the bromine. So the methoxide could grab that, and electrons come down, and out goes the bromine. And if that worked, which it would, I would have a CH3 down. Didn't do anything with that, right? And a double bond right there, and then a CH3 coming out. So unwinding that so it actually looks normal, it is going to have the, so here's where the bromine was. Here's where that CH3 that was next door to it is. The double bond would be right there. And then the other one didn't get touched, and it's just up here. Nothing happened there. So that would be my product of the E2. So with the bromine coming at me, and I do an E2, I'm going to end up with the double bond at the more substituted position, or the Zaitsev double bond. Let's see what they said I actually got. Going back to what they say is true. Let's go back up. Whoa, that was a bad thing. Didn't exactly want to move that. Let me undo this a couple times. There we go. I don't think it's going to let me roll the whole thing, but if you look back at the problem, you can see that looking at the E2 reactant or product that they show, that they give this. They give this as the product. Double bond there, methyl there. So that's not what I get when the BR is forward. So this is the wrong product, right? It's not the result that I should have gotten. So what this then tells me is that my bromine should be going the other way. So I'm going to try the other one. So if we do that, let's try this guy. So the CH3's up, CH3's down, and I'm going to try the bromine going back, like that. So with the bromine going back, do the chair form. We'll put the bromine axial, because that's where it has to be. Now, the CH3 right next door to it is trans to it. So if the bromine's down, the CH3 is now up here. And the other CH3 is also trans to it. So 1, 2, so the CH3 at the back, that back carbon, it's also going up. And so that puts it in an equatorial position. So I'm going to draw in the H's. Let's do them in black. 1 H is here. 1 H is here. 1 H is there. The H that is 180 degrees apart or away from the BR is that H right there. That's the only one that will work. The others are all in an equatorial position and they're 60 degrees. So just the highlighted H will work. So when I remove that with my base, so we have OCH3 minus, come and grab it. Those electrons flip down. Bromine's gone. It is going to look like this in a chair form. We'll leave it in a chair for right now. Here's a C. Here's a C. And the double bond is right here. So when that should say given, huh? So when I go and unwind what that thing looks like, 6-membered ring, and the methyls, there they are, right? They didn't change. And the double bond is actually right there, which is exactly what they said happened. So I know that it looks like that right there. That has to be it, that the bromine was actually going away. I tested out coming towards me, and it didn't give me the answer I want. So the bromine is actually going away from us. Okay, and they did ask if it is going to be R or S. And let's see. I think that it ends up being an S, but let's just check that out. So bromine is number 1. And there's a hydrogen coming at us, right? There's the H, it's number 4. So I know it's in the wrong spot. I'm going to have to reverse my reading. And the part of the ring going towards that first branch is 2, and that is 3. So it is showing, as it's written, as being clockwise. It's showing as R, but the H is in the wrong spot. And so this is actually an S. It's an S stereocenter. So what you do literally is you just take that bromine, park it in one position, cross your fingers. If you're unlucky like I was, do the other one. Okay, so the bromine is in fact supposed to be in the trans position to those two CH3s. Now it says, explain why the two reactions resulted in different products. The reason for that is that, you only got the one product in the E2, and that's because it's the only one you could get. With E1, which was the second possibility that we had, with that E1 reaction, the leaving group was gone by the time the elimination occurred. And so since the leaving group was actually gone, then we didn't have the anticoplanar problem. We didn't have to pick just one hydrogen, and the hydrogen that gave the most stable Zaitsev product could easily be removed. So we got both. The major one was the Zaitsev, just because we weren't tied by that anticoplanar idea. I just noticed when I went to publish this, all the writing was fine and the things are lined up okay, but I noticed that the question had shifted down. And so when you look at the end of the last, the main recording, the labeling E1, E2, all that got shifted around. So I just went and shifted it back. So this is the actual picture that you guys want to focus on. Okay, you kind of saw it shift around in there somewhere, so I just fixed it.